A geochemist named Clair Cameron Patterson spent years trying to answer a question that had haunted scientists for centuries. And in 1956, he finally succeeded. The number he calculated, 4.55 billion years, didn't just rewrite geology textbooks, because it revealed something far more unsettling about the connection between ancient meteorites and the atoms sitting inside your skeleton right now. Those atoms share the same origin and the same age, which means the method Patterson used to figure this out applies directly to you. Most people assume that dating ancient objects involves sophisticated guesswork or educated estimation, maybe some math that could drift off by a few million years here or there. That assumption is completely wrong. Patterson conducted atomic forensics, and the same techniques that tell us when a rock formed now catch wine counterfeiters and art forgers trying to pass off fakes as masterpieces. The universe leaves evidence everywhere it goes. And once you learn how to read that evidence, you realize scientists aren't estimating anything at all. They're conducting a criminal investigation on reality itself. Here's what most people get wrong about the age of everything. They treat it as an abstraction, some theoretical number cooked up in a laboratory that has nothing to do with their actual lives. The age of everything is written into everything around you, buried in the ground beneath your feet, encoded in the carbon atoms, woven through your DNA, and traveling toward you right now as ancient light from the edges of the observable universe. The cosmos keeps receipts in the form of atomic signatures, and reading those signatures has become one of the most precise measurements in all of science. The story begins in 1896, when a French physicist named Henri Becquerel was investigating a phenomenon that had the scientific world buzzing. Wilhelm Röntgen had discovered X-rays just months earlier, and Becquerel hypothesized that uranium salts might emit similar rays after absorbing sunlight. He designed an experiment that involved wrapping a photographic plate in black paper, placing uranium salts on top, and leaving it near a window to soak up the sun. Paris had other plans for him because cloudy skies persisted for days without a break. Becquerel figured the experiment was ruined, so he tossed the wrapped plate and uranium into a drawer to wait for better weather. A few days later, for reasons historians still debate, he decided to develop the plate anyway. And there on the film was a clear, sharp image of the uranium crystals burned right into the surface. No sunlight had been required at all. Something was radiating out of those atoms spontaneously and continuously without any external trigger. That accidental discovery of radioactivity handed scientists the keys to the entire history of the cosmos. Becquerel had stumbled onto something without fully grasping what it meant, because atoms are not eternal the way people assumed. Certain atoms are unstable and they decay, transforming into different atoms over time at rates that are absolutely unalterably constant. Nothing changes these rates, not temperature, not pressure, not chemical reactions, and not the gravitational field of a nearby planet. The decay rate of a radioactive isotope is fixed by the fundamental constants of nature themselves. Consider what that means for measuring time. If you have a clock that ticks at a constant rate, you can use it to measure duration. Radioactive atoms function as clocks, trillions of tiny atomic clocks embedded in every rock and every fossil and every ancient scrap of the universe. Those clocks started ticking the moment they formed and have been counting down ever since, which meant the breakthrough was simply learning how to read them. Ernest Rutherford saw the implications first in 1904. He realized that if radioactive elements decay at known rates, and if you could measure how much of the original parent element remained versus how much daughter product it had decayed into, you could calculate exactly how long that transformation had been happening. You could determine when the rock crystallized and when the clock started, which gave you the age of the sample itself. Uranium-lead dating works like this. Uranium-238 is radioactive, and over time it transforms through a chain of intermediate decay steps into lead-206, not ordinary lead, but a specific isotope. This transformation happens with a half-life of 4.47 billion years, meaning every 4.47 billion years, exactly half of any uranium-238 sample will have become lead-206. The laws of quantum mechanics guarantee this with statistical certainty across large numbers of atoms. Not approximately half, or usually half, but exactly half every single time. Finding a rock and measuring the ratio of uranium-238 to lead-206 locked inside its crystal structure tells you everything you need to know. A 50-50 ratio means that rock crystallized 47 billion years ago. More lead than uranium indicates something older, and more uranium than lead points to something younger. Reading the atomic clock that has been ticking inside that mineral since the moment it solidified requires no guesswork at all. Clair Patterson spent years at the California Institute of Technology perfecting this technique. And his problem wasn't the physics, but the contamination. Lead exists everywhere in the modern environment, and even microscopic amounts would throw off his measurements completely. Patterson had to build the world's first ultra-clean laboratory and remove every trace of environmental lead just to get accurate readings from ancient meteorites. Those meteorites were fragments of asteroids that formed at the same time as Earth from the same primordial solar nebula. And they gave him his answer of 4.55 billion years for the age of the solar system and the age of Earth. His work was so careful that his number from 1,956 has barely shifted in 7 decades of subsequent measurement, refined only slightly to 4.54 billion years plus or minus about 50 million. That level of precision, knowing our planet's age to better than 1%, is measurement rather than estimation. Uranium-lead represents just one atomic clock among dozens available to scientists. Potassium-40 decays into argon-40 with a half-life of 1.25 billion years, making it perfect for dating volcanic rocks and establishing the ages of geological formations. Rubidium-87 transforms into strontium-87 over 49 billion years, useful for the oldest rocks in the cosmos. Carbon-14 decays into nitrogen-14 with a half-life of just 5,730 years. And Willard Libby won the Nobel Prize in Chemistry in 1960 for developing radiocarbon dating, which revolutionized archaeology overnight. Different clocks serve different timescales. So dating a wooden artifact from ancient Egypt calls for carbon-14, while dating a lava flow from 100 million years ago requires potassium-argon. And dating the oldest zircon crystals on Earth, found in the Jack Hills of Western Australia, demands uranium-lead. The part that should give you confidence in all of this is how these independent methods cross-check against each other. When multiple radioactive systems in the same sample, systems based on completely different elements with completely different half-lives, all produce the same age, you know you've found something real. This isn't one line of evidence, but a chorus of atomic witnesses, all testifying to the same history, and when that happens in science, you take it to the bank. Carbon dating deserves a closer look, because most people have heard of it without understanding why it works so well. Carbon-14 forms continuously in Earth's upper atmosphere when cosmic rays from deep space, high-energy particles streaming in from ancient supernovae and other violent cosmic events, slam into nitrogen atoms and transform them into carbon-14. This radioactive carbon gets absorbed by plants during photosynthesis. Animals eat the plants, and the carbon-14 spreads through the entire food chain. Right now, there's carbon 14 inches, your muscles and your bones and your brain, making you slightly radioactive along with everyone else on the planet. The key is what happens when an organism dies and stops taking in new carbon, because the carbon-14 already present begins to decay on its countdown. After 5,730 years, half of it is gone. After another 5,730 years, half of what remains disappears, and this continues predictably forever. Measuring the ratio of carbon-14 to stable carbon 12 inches as an ancient sample and comparing it to the ratio in living organisms tells you exactly when that sample stopped breathing. Here's something most people don't know that shows how these techniques reach far beyond ancient history. After the nuclear bomb tests of the 1950s and early 1960s, atmospheric carbon-14 levels spiked dramatically and actually doubled in concentration. That pulse of bomb-generated carbon-14 got absorbed into everything growing during that era, including plants and trees and grapes, which creates an accidental timestamp in the historical record. When someone tries to sell a bottle of supposedly vintage 1945 Bordeaux for thousands of dollars, forensic scientists can test the wine itself and check for bomb pulse carbon-14 that shouldn't exist in a pre-war vintage. Nuclear forensics now meets fine wine authentication, and the same physics that illuminates ancient Egypt catches modern counterfeiters red-handed. Art forgery detection works the same way, because paintings supposedly created before 1950 shouldn't contain certain isotopic signatures that only exist as a result of nuclear testing. A Van Gogh canvas shouldn't have bomb carbon in its fibers. And these atomic clocks don't just measure deep time, but have become tools for criminal investigation in the present. What connects all of this is that the radioactive decay, allowing us to date ancient scrolls, operates on the same physics powering nuclear reactors. The same physics explains why the sun has been shining for 4.6 billion years without burning out. And the same quantum mechanics governs the behavior of atoms inside your smartphone. The universe doesn't maintain separate rulebooks for different situations, and that universality is why we call them laws. People often ask how we know the decay rates haven't changed over billions of years, wondering if physics operated differently in the distant past. Scientists have tested this directly by examining the spectral lines of light from distant galaxies, light that departed those galaxies billions of years ago, and those spectral signatures match what we observe in laboratories today. The fundamental constants haven't shifted, and what worked 10 billion years ago works now, because the universe has been playing by the same rules for its entire existence. If those rules had ever changed, we would see it written in the light. The question of the universe's own age takes everything to a much larger scale and into philosophically strange territory. Looking at a star 1,000 light years away means the light entering your eye departed that star 1,000 years ago. So you're not seeing the star as it exists right now, but as it existed a millennium in the past. Looking outward in space is literally looking backward in time. And the farther away something is, the older its light when it reaches us. The most distant galaxies observable with the James Webb Space Telescope sit over 13 billion light years away, meaning we're seeing them as they existed when the universe was less than 1 billion years old. Those are baby galaxies still in the process of formation, chaotic and bright and strange, compared to the mature structures we see closer to home. We're watching the childhood of the cosmos frozen in light that's just now completing its journey to our detectors. Edwin Hubble discovered something that changed everything in the 1920s, when he observed that distant galaxies are moving away from us in every direction. The farther away a galaxy sits, the faster it recedes, because space itself is expanding, and the fabric of the cosmos is stretching while carrying galaxies along with it like raisins rising in bread dough. Running that expansion backward reveals that if everything is flying apart now, then in the past everything was closer together. Keep rewinding and everything was closer still, until going back far enough shows all the matter and energy in the observable universe concentrated into an incomprehensibly dense hot state. A Belgian priest and physicist named Georges Lemaitre proposed this idea even before Hubble made his observations, calling it the hypothesis of the primeval atom and suggesting the universe had a beginning and a birthday. Measuring how fast space is expanding and calculating backward reveals when that expansion started, and the answer, refined through decades of increasingly precise observation, is 13.8 billion years for the age of the observable universe. Direct evidence came in 1965 when two radio astronomers at Bell Labs in New Jersey named Arno Penzias and Robert Wilson were trying to calibrate a sensitive antenna for satellite communication. They kept detecting a persistent background hiss that they couldn't eliminate no matter what they tried, and they even climbed inside the antenna and removed pigeon droppings, thinking that might be the source. The static was coming from everywhere across the entire sky, and what Penzias and Wilson had accidentally discovered was the cosmic microwave background radiation, which is the afterglow of the Big Bang itself. This is light from the early universe released about 380,000 years after the Big Bang, when the cosmos finally cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was an opaque plasma fog where light couldn't travel freely, and then transparency arrived suddenly and the first light was released. That light has been traveling ever since, stretched by 13.8 billion years of cosmic expansion, from visible wavelengths all the way down to microwaves. The Planck satellite launched by the European Space Agency mapped this ancient light with extraordinary precision, and the patterns in it reveal tiny temperature fluctuations showing density variations in the infant universe that match our theoretical predictions almost perfectly. The age calculated from the cosmic microwave background agrees with the age calculated from the expansion rate, providing independent methods that arrive at the same answer. Old analog television sets displayed something remarkable without anyone realizing it, because about 1% of that static noise was the cosmic microwave background radiation. Viewers were seeing interference from the birth of the universe coming through their TV sets, ancient light older than any star currently shining, mixed with their evening broadcast. Every glance at the night sky is a look at history, because the light from Proxima Centauri is 4 years old, and the light from the Andromeda Galaxy has been traveling for 5 million years. Some photons, captured by our most powerful telescopes, began their journey when the universe was a fraction of its current age. The change in perspective comes from realizing you are not separate from this timeline at all. The atoms in your body, including the carbon and oxygen and nitrogen and iron, were manufactured inside ancient stars that lived and died billions of years before Earth existed. Those stars fused hydrogen into helium and helium into carbon and carbon into heavier elements, all the way up to iron in their cores. And when massive stars exhausted their fuel and exploded as supernovae, they scattered those enriched elements across space. Even heavier atoms like gold and platinum and uranium required something more violent in the form of neutron star collisions, which are the corpses of already dead stars spiraling together and smashing at a significant fraction of the speed of light, while releasing more energy in seconds than our sun will produce in its entire lifetime. The gold in your jewelry was forged in cataclysms that briefly outshone entire galaxies. The phrase about being made of star stuff has become so common that people nod along without feeling the violence behind it. You're made of cosmic wreckage, the debris of multiple stellar generations processed through nuclear fires and apocalyptic explosions, collected by gravity into a new solar system, assembled by chemistry into complex molecules, and organized by evolution into something that can look back at the stars and figure out where it came from. That's not poetry, but your actual biography. Carl Sagan created the cosmic calendar to help people feel these timescales, and it remains one of the most powerful tools for grasping deep time. Compressing the 13.8 billion year history of the universe into a single calendar year puts the Big Bang at midnight on January 1st, and the Milky Way galaxy doesn't form until around March. Our sun and solar system appear in early September, while life on Earth begins in late September. Dinosaurs roam during the Christmas holiday and go extinct on December 26th. And the entire history of our genus Homo, from the first upright ancestors to this conversation, occupies only the final day. All of recorded human civilization, from ancient Sumeria to the smartphone in your pocket, happens in the last 14 seconds before midnight on December 31st. Another way to feel that scale is to imagine the age of the universe as the distance from New York to Los Angeles, because all of human civilization would fit in the final quarter inch before reaching the Pacific Ocean. Somehow, in that cosmic eye blink, we figured out how to read the clocks by measuring radioactive decay in ancient zircons and detecting stretched light from the beginning of time and calculating the expansion of space itself. We reconstructed the history of the cosmos using evidence the universe left behind, and most people walk around on this ancient planet beneath this ancient sky while constructed from ancient atoms, completely oblivious to the temporal depth surrounding them. They think age is something that happens to individual people through lines on a face and gray in the hair, without realizing that age is woven into the fabric of existence. Time is physical, and history is written in rock and radiation and light, which means every atom is a witness to events that predate our world. An ongoing mystery exists in all of this, because different methods of measuring the universe's age give slightly different answers. The expansion rate measured from nearby supernovae doesn't perfectly match the rate implied by the cosmic microwave background, and cosmologists call this the Hubble tension. The discrepancy is small at just a few percent, but it persists stubbornly, and it might be measurement error, or it might be something we don't yet understand about the universe. This is live science, and the story isn't finished. That unresolved mystery captures the point entirely, because we're not handed these answers from on high, but earn them through careful measurement and cross-checking of independent methods and following evidence wherever it leads, even when it leads to contradictions we can't yet resolve. That's how science actually works, not by proclaiming truth, but by interrogating nature until nature confesses. The next time you pick up a rock and feel its weight in your hand, consider that rock may have been sitting on this planet for billions of years, with atoms assembled in the solar nebula before Earth even formed. The atoms in your hand share the same origin from the same ancient cloud of gas and dust, making you and the rock distant cousins, both descended from a stellar nursery that collapsed under gravity 4.6 billion years ago. That's what the age of everything really means. Not just dates on a timeline or numbers in a textbook, but a revelation about connection and the depth beneath ordinary surfaces. The universe preserves its own history in atomic ratios and ancient light, and the cosmic microwave whisper still arriving from everywhere at once. This is a universe that encodes its past so precisely that creatures on a small rocky planet, creatures who've existed for an eye blink of cosmic time, can reconstruct the entire story from the beginning. We're not separate from that story, because we're the latest chapter, made of ancient materials and powered by a middle-aged star and carrying atomic clocks in our very bones. Against all odds, we learn to read them.